students, welcome to class. Today's lesson is all about investigating graphs of polynomial functions. And so our two learning goals are, first of all, with only the degree and sign of the leading coefficient, we're going to learn how to determine whether a function is an even function or an odd function, and we'll also learn how to determine its what's called end behavior. And secondly, we'll be identifying and using maxima and minima of polynomial functions to solve problems. So at this point, I'm going to show you a little video clip with Dr. Berger, kind of explaining a little bit about the different types of graphs you see in this table.
You know, if you see a polynomial function, it turns out that without doing all the complicated work that sometimes we see in order to create a very accurate graph of it or to actually find the zeros of it, we can just casually look at it and actually get some insight into the picture, into the graph associated with that function. Let's take a look at an example, a polynomial function, and see that we can say a lot. Here's the polynomial function p of x equals negative x cubed minus 2x squared plus x plus 5. All right. Well, there's lots of terms there, and it seems sort of, I don't know, maybe threatening. And it turns out that all those terms are relevant and important if you want to produce a very accurate graph associated with this particular function. But if you want to forego the accuracy but get sort of a rough feel as to what this thing might look like, it turns out all you've got to do is really look at what's going on the very highest power. So we look at the degree of the polynomial defined to be the highest power on all the x's. In this case, we see that this is a cubic because the highest power is 3, x cubed. And it turns out that you can tell lots by looking at that term. In some philosophical sense, that sort of dictates, that's the dominating term to figure out what the global structure of this graph is going to look like. And so we can actually see that by, first of all, just looking at what happens as we have different powers. So it turns out if we have degree 1, the degree is what we call the highest power in the polynomial. So this is of degree 3, for example. Degree 1 would mean that we just have something that looks like that. Highest power is the invisible 1. Well, we know that's a straight line, and so we're talking about a linear function. It might not look exactly like this. It could be any kind of linear function. If we have degree 2, so if it looks something like that, then we have a quadratic, and then we have a parabola. And again, this is just a generic parabola. It could be any place all over. It could be even pointing down. If we have degree 3, we're going to potentially have sort of 2 bends, 1, 2 bends. That would be degree 3. Degree 4 might have as many as 3 bends, 1, 2, 3 bends. Degree 5 might have as many as 4 bends, 1, 2, 3, 4. So for example, if someone showed me this graph, I would never guess that it was a degree 3, a degree 2, or a degree 1 polynomial because it has too many bends. So just by looking at this, I can actually say that it might look something like this. Now, of course, the leading coefficient, that's the coefficient that's in front of the x term with the highest power, in this case, x cubed. In this case, we see it's a negative 1. Well, the negative 1 actually tells us, in some sense, at least the sign, whether this thing is sort of a happy-faced thing or a sad-faced thing. Well, we've seen sort of happy-faced parabolas and sad-faced parabolas, and we've seen there that that's determined by the sign of the coefficient on the x squared term. But it turns out that's true with all of these. Of course, they don't look like happy faces anymore, although you can think of them as happy faces. If A, the leading coefficient, is positive, and we have an odd degree, then in fact it's going to have this sort of general shape where we start off way down here on the left at kind of negative infinity and sort of rise up to positive infinity. We might have wiggles in between, but the end result is going to be up to positive infinity. And with even degrees, we're going to have that smiley face type picture. There might be some little vibrations going on here. We might sort of go back and forth, but the ends are always going to be pointing up, happy. However, if we have a leading coefficient that's negative, then in fact we see sort of the flip of this over the x-axis. So as we go off to the left, we see that this is going off to positive infinity. And as we go off to the right, we see now we're dropping to negative infinity. And similarly, with even degrees, we have sort of a frowny face as we look toward the ends. So here, what I can see is that this is a cubic degree 3 polynomial. Leading coefficient is, in fact, negative, and so the picture is going to be something like this, although there might be a little bit more dramatic, loopy kind of thing. I see this is the general sense of the picture. What about this? This I see as a polynomial of degree 8. I see 8 is even, and so since it's even, I know that it's going to be something that looks like this. There might be a lot of wiggles in between, but I know that since we have a leading coefficient of 5, and 5 is positive, then I see that, in fact, it's going to end up being a smiley face, even though in between there might be some dental work required. Anyway, just by looking at the degree of the polynomial, the power on the highest power of x, we get a sense of what the graph might look like. And looking at the coefficient in front of that, also known as the leading coefficient, we can tell if the thing is a happy-faced or a sad-faced graph.
Okay, so now that you got to see a little bit about these different graphs, let's take a look at each one of these types of graphs individually. This first graph, this graph that looks like a line, is just that. It is a linear function, and it would be a degree 1 equation. The second one is probably also very familiar. That's quadratic, and it, of course, is degree 2. We've studied those a lot. The third one is a cubic function, and it's degree 3. The next one is a quartic function, and so the degree is 4. And finally, the quintic function, and it has degree 5. Now, in the little video clip, you learned something about the behavior of these functions. And it was basically categorized by whether it was an odd function or an even degree function. So let's first take a look at all the odd degree functions. So I've highlighted all of the odd degree functions. They are the linear, the cubic, and the quintic, because the degree is of each one of these is an odd number. Now, one of the things that Dr. Berg talked about in the video is how the end behavior goes for an odd function. For an odd function, your ends will go in opposite directions. So for instance, with the linear, one end is going up, pointing upward, and the other end is pointing downward. For the cubic function, the same thing. On the one end, like on the left-hand end, the graph was pointing downward, and on the right-hand side of the graph, it's pointing upward. Now that could be in reverse. Say on the left-hand side of the y-axis, it could be pointing up, but then the right-hand side would have to be pointing down. Odd functions, their end behavior, they're always going to travel in opposite directions. So you can think of odd and opposite, so your ends will travel in opposite directions. And you can see the same thing is true here for this quintic function. And if you just look at the left-hand side of the graph, so if you look out from the y-axis going to the left, it's pointing down. Look at the graph going to the right of the y-axis, it's pointing up. And again, it could be flip-flop, so that on the left-hand side it was increasing or going up, but then to the right might be going down then. But they'll always go in opposite directions. Now next I've highlighted the two even functions that we have in our table. Now there's certainly other even functions and other odd functions, but the two smallest degree ones would be the quadratic and the quartic. And notice the graphs of these even functions, the end behavior agrees. So on either end of the graph, they're going to go in the same direction. So for instance, on this quadratic, since it's facing up, both of the ends will face up. If the parabola was opening downward, then they'd both be facing downward. But they're in agreement. They're both going in the same direction on the ends. Same thing with the quartic. So this one is a quartic function that's facing upward, and so both of the ends are facing up. Almost you can kind of imagine it being like a smiley face. Well, it's kind of a really goofy smile. The quadratic one looks much more like a smiley face, but you know, you can, because the ends of the mouth, if you will, are facing in the same direction. It's either smiling or it's frowning and it's facing downward. Now in the video we also saw why that might be. Why might both ends be facing upward or both facing downward? Well, that has to do with the sign on the leading term. So in this table we're going to do a little summary about the effect of the leading coefficient or the leading term, which we're going to call A. Okay, so I went ahead and created some little coordinate planes here. And I'm going to sketch some graphs of some odds and even functions. So if I wanted to draw an odd function that had a positive a value, then when I think about a positive a value on an odd function, well, first of all, I know the ends are going to go in opposite directions because it's an odd function. So when I think about a positive a value and I want to know which kind of direction this is traveling, I think about as I'm going to the right of the y-axis, if it's a positive a value, I want that part to face up. So as I'm moving to the right, the furthest point to the right should be facing up. And so a cubic function would be a good odd function to look at, and a cubic function that would have a positive a value would look like this. And see, what I meant is over here on the right hand side of the y-axis, see how that part of the graph is facing upward. And so that's how I know that's a positive a value. And when that happens, then this is how we would describe the end behavior to the right of the y-axis. So we would say as x values are approaching positive infinity, so in other words, positive numbers getting bigger and bigger and bigger, then we would say that the function, which we call p of x, we would say that p of x would be approaching positive infinity as well, because it's increasing and getting higher. Now on the other side of the y-axis, we would say as the x values were approaching negative infinity, in other words, as they're going to the left, see, like going like this way, as we were going towards negative infinity, then the values of the function p of x are increasing negative infinity. And that's because it's going down. Now if I wanted to look at an odd function here, but the one that would have a negative a value, in other words, a negative number in front of that, if I was doing cubic, in front of the x cubed term, then that cubic graph would look like this. As I was going to the right of the y-axis, that part of the graph would be decreasing, so it would be looking like something like this. And again, as I'm to the right of the y-axis, this graph is actually decreasing. And so we would say that over on the right-hand side of the y-axis, in other words, as the x's were approaching a positive infinity, then the function p of x was approaching negative infinity. In other words, it's getting smaller. They're going down. Over on the left-hand side of the y-axis, so in other words, as the x values are getting smaller and smaller, in other words, as the x values are approaching negative infinity, then the value of the function is actually approaching positive infinity because it is increasing. You'll see that right here, it's actually going up over here. Now this is what we call describing the end behavior. So when we look at end behavior, we look at where the ends of the graph are, the one on the left-hand side of the y-axis and the one on the right-hand side of the y-axis. And when we describe end behavior, we say what's happening to the function as the x values are getting bigger and bigger and bigger, in other words, as we're going towards positive infinity. And then also we describe when we're going the opposite direction, as the x values are getting smaller and smaller, so more and more negative, what's happening to the value of the function p of x. So what about an even function? Well, the most basic even function would be the quadratic. So let's take a look at the quadratic. And a quadratic that would have a positive a value out in front would be a parabola that's going to open up like this. And you may remember back the significance of that negative out in front of the x squared. If there was a negative, it faced down. If it was a positive, it faces up and makes a smiley face parabola. So if I wanted to describe the end behavior to the right-hand side of the y-axis, I would say something like this. As x is approaching positive infinity, then the function p of x is also approaching positive infinity. And the reason why that is again, as we're going to the right of the y-axis, the graph is increasing over here. And then if we went on the other side and we said as x is approaching a negative infinity, then p of x is approaching positive infinity. And again, this is because the graph is increasing on this side. Again, it's going up. Now, notice what I said about even functions. The ends will always be in agreement. And so you can see what I mean by agreement here is, see how in both cases the functions are going towards positive infinity on both sides of the y-axis. And so they're said to agree. Now, if I had an even function like a parabola that has a negative a value, in other words, the leading term is negative, that's going to be your typical sad face parabola, like this. And so to describe its end behavior to the right of the y-axis, we would say as x is approaching positive infinity, then the function itself is actually decreasing, which means we'd say it's going towards negative infinity. In other words, it's a decreasing function to the right of the y-axis. And then over here on the left-hand side, we would say as x is approaching negative infinity, in other words, as we're going to the left, then the value of the function is approaching negative infinity as well. So again, there's that agreement between the function. It's approaching in both cases a negative infinity. There's agreement there. So there's the significance of the leading coefficient of A, whether the graph is going to, as you read to the right of the graph, whether it's going to face up or down. And then also, if it's odd or even, it'll tell you whether the ends will be in agreement, in other words, traveling in the same direction, or whether they'll be going in opposite directions. So let's go ahead and try an example. So I have this function, and it's negative x to the fourth power plus 6x cubed minus x plus 9. And I know that the leading coefficient is negative. It's actually negative 1, and that means it's a negative number. I know that the degree is 4, which is an even number. And so even though I don't know what this graph looks like, I haven't put it in my graphing calculator yet to see what it looks like, I know it's going to be something like this one maybe up here, because it's quartic, so it's going to be something like this one right there, except for it's going to face down. So because, it's got a negative leading coefficient, so it's like it's going to be that squiggly kind of facing downward, and so it would maybe be something like this. I could graph it in the graphing calculator to see, but this is sort of going to be the trend. Both of the ends are going to face down, and it could look something like this. But to be certain, we could actually put it in the graphing calculator, and so I'll see what that looks like just a minute. Okay, so this is what it actually looks like. And so to describe the end behavior, first of all, we're going to look as x approaches negative infinity, which means that what we're really doing is we're looking starting at this y-axis and we're going this way. And what we can see is that as we're approaching negative infinity, the function is decreasing, so it's approaching negative infinity as well. And then if we wanted to look over where its x values are approaching positive infinity, in other words, values of x are getting bigger, we go to the right of the y-axis, and you can see that, of course, then the graph is facing down as well, so it's approaching negative infinity. And remember, this is an even function. The leading coefficient is negative. Right here it was a negative 1, right? And so these are in agreement and approaching negative infinity. Let's go ahead and turn the page. Okay, so I went ahead and graphed this next function, 2x to the fifth plus 6x to the fourth minus x plus 4. And so first of all, I want to look at the leading coefficient. So the leading coefficient is 2, and that's a positive number. And so I'd want to write that the leading coefficient is 2, and that means it's positive. So positive. The degree is 5. So it's a quintic equation, and so that's an odd number. So we know that odd functions must travel in opposite directions, and we can clearly see that that's what's going on here. So we've got one branch over here that's facing downward. We have one branch over here that's facing upward. And so it really does follow that behavior that we saw when we looked closer at each one of those different types of functions. Now, to describe the end behavior, I would start off, I could look at when we are going to the left of the y-axis, in other words, over this direction. So if I was traveling this way, away from the y-axis, I would say, so as x is approaching negative infinity, then I could say p of x, the function, in other words, is approaching negative infinity because it's going down. And then I could also then look at the opposite direction, so going this way towards positive direction, then I could say that as the x is approaching positive infinity, then the function p of x is approaching positive infinity. And that's because it's going up over there to the right. And so it again fits that pattern of that the ends are going in opposite directions. So we're going to go ahead. We've done a few of these together, and C is very similar to this one. So what I want you to do is try C as a you try question. And so you'll have to grab out your graphing calculator and type that in, maybe adjust the window a little bit so you can, what I did is I just went to under window and just kept changing the y, min, or max so I could see the whole thing, at least to see where, the bends reached a maximum and minimum. And then just describe what's going on here. Tell what the leading coefficient is, whether it's positive or negative, the degree, and then describe the end behavior. So go ahead and pause the video now and take a look at example C. Okay, so what you probably found out is that this graph was very similar to the one in example B, and in fact the leading coefficient is the same. It's 2 and positive, degree is 5, which is odd, and that means that the end behavior will be identical. And so really just it's a duplicate basically of example B. So let's move on and look at example 2, where I have provided some of these graphs, and we're going to do a little more analysis of these polynomial functions. Okay, so let's take a look at this graph. So right away, I hope you can tell that this graph is, it's an odd function. So it's got to be, you can see they're going in opposite directions, the ends. So this is going to be an odd function. So it wants to know, is it odd or even? So it's odd. And as x is approaching negative infinity, so if we're going this way, away from the y-axis, you can see that the graph is increasing. It's going up. So it's approaching positive infinity. It's increasing. And then as we go the other direction, so as we're, y values or x values are increasing, so in other words, as we're approaching positive infinity for the x values, then the graph is going down. So that means we're going towards negative infinity. And so there again, you see how this odd function, the ends, behave in opposite directions. They go in opposite directions. Now, if we wanted to know the degree of this, we have to take a look at the number of turns that this graph takes. Now, notice the graph turns there, 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 and there. And see how it changes directions 4 times. And so if it changes directions 4 times, that means that there are 5 different segments of the graph. And that means that this must be a degree 5. And I actually think what they wanted us to do is write odd here. So odd degree, but it specifically is 5th degree. It's a quintic function. And we can tell that its leading coefficient is actually negative. And here's how we know that. Because if we look at the part of the graph that is to the right of the y-axis, so I'm going to highlight that here. So I'll highlight it in blue. So if you look at that graph, the end part of it is decreasing. And so as we're looking to the right, that portion of the graph is facing downward, and so it must have a negative leading coefficient. Okay, what about this next one? Well, this one is clearly an even function because you can see that the ends are in agreement. They're both facing the same direction. They're both facing up. So that also will tell us whether this has a negative or positive leading coefficient. It actually has a positive leading coefficient because, again, as we're looking to the right of the y-axis, the graph is increasing. It's facing up. It's like a smiley face, kind of a really crooked smile, but a smiley face graph. And so this is clearly a positive graph. And then if we talked about end behavior, we could say as x is approaching a negative infinity, that means to the left of the y-axis, then the function's value, p of x, is approaching positive infinity. It's going up. And also as x is approaching positive infinity, as we're going to the right of the y-axis, then the function's value is heading towards positive infinity as well. So that would describe its end behavior. So why don't you go ahead and give C a try. This is a you try question. Tell whether this is an odd or even function, whether it's got a positive or negative leading coefficient, and then describe the end behavior to the left of the y-axis and to the right of the y-axis. In other words, towards positive infinity for x and towards negative infinity. So pause the video now and try example C. Okay, so that function was odd and negative leading coefficient, and this is what the end behavior looks like. So let's go ahead and turn the page. Okay, and so in one of those prior examples, I talked about the turning points on the graph. Well, those turning points are called local minimum or maximums. So see on this graph here, there's a turning point where the graph is changing directions from either increasing to decreasing or vice versa. And see how that happens there? It happens right up here. It happens again right down here, right? Oops, right in there. And then right up here. So this actually changes directions those 4 times. Oops, I'm not get that highlight. And so each of those places represents either a local maximum or a local minimum. Now why we call it local is because, for instance, this point right here, that is not actually an absolute maximum because there are certainly y values that are higher than that because they continue on to infinity to the left of the y-axis, you know, forever. So, but it's local, so it's the maximum value in that location, in that area. So it's called a local maximum. So we would define a turning point to be where the graph changes from increasing to decreasing, or vice versa. Could be from decreasing to increasing. A local maximum or minimum is a point on the graph where there's a turning point. And if the graph is turning from decreasing onto increasing, then that will create a minimum point as it's turning from its decreasing to increasing position. So on the graph, I've marked here in purple local minimums. So local minimums are right here on the graph and right here. And of course you can see they are turning points. And then the local maximums also are turning points on the graph, and they are here and here. I'm going to show you a little video on how to use the graphing calculator to, if you had a graph of a polynomial function, how you could use the calculator to determine what these local minimum and maximum points are. Okay, so we're going to take a look at how to find maxima and minima with the calculator. And the first thing we need to do is we're going to take a look at example A, and we're going to type in that equation into the y equals menu. So that equation is 2x to the third power minus 18x and then plus 1. And so we kind of have an idea of what this is probably going to look like. We've been studying these cubic graphs. So we hit the graph key and kind of see what that looks like on the large screen. And this is kind of just looks like a bunch of, almost look like vertical lines. Well, when you see something like this, what that means is you probably are going to need to adjust your window some. It looks like that the graph goes up higher than what we can see in a standard 10 by 10 and lower than we can see. And so what we're going to want to do is we want to go to the window. So we hit the window key. And let's change it so that we can get it to go up a little higher. It also looks like it doesn't go too far to the left or to the right. So we could change maybe the x-min to -5 and the x-max to maybe just 5. Keep it scaled by 1s. But maybe for the minimum for the y, maybe we want to go down to -25. We'll see how that's looking. Okay, and then maybe go up to +25 on the y max. We'll just kind of see if we need to adjust from there. Okay, and so press enter, and if we hit graph again, let's see what that looks like. And that looks much better. Now we can actually see these places that would represent the local maximum and the local minimum. And so here's how we could actually use the calculator to find those max and min points. So if we hit the second key and the trace key, it's going to take us to this menu where you can see, if you go down to 3, there's minimum. So if we select that, press enter, and we go back to the screen, you'll see that the cursor is blinking. And the minimum is going to be the one that's here to the left of the y-axis. So if we were to just scroll on the graph here, you can see the cursor is moving. And it's asking us a question at the bottom of the screen. It's asking us to determine a left-hand boundary. So what that means is we want to make sure our cursor is on the left-hand side of where we see this minimum value being, and this change in direction. And so we just go somewhere on the left. It doesn't really matter where, just as long as you're on the left-hand side. And we press enter to establish a lower bound. And you'll see that little arrow that's pointing to the right that came up. So it's saying we're going to start looking for this minimum value here. And now it's asking for a right bound. So now we got to continue scrolling on it. We're going to scroll so that we go past that minimum and stop anywhere to when we get to the right. Here's fine. Press enter, and notice another arrow goes up, and they're pointing towards each other. And what that means is it's saying I'm going to start here at this left arrow, and I'm going to travel along the graph to this right arrow, facing arrow, and actually it's facing to the left, but the one on the right hand side, and we're going to look for the very lowest output value, the lowest y value that we can find in that interval. So it's asking, do you want to guess? And I guess you could, if you wanted to, kind of scroll down to where you were thinking, where you thought, the minimum was. This looks like it's maybe the minimum right there. And so we might want to use that as a guess. So we press enter, but then it's actually going to take us to exactly where the minimum is, or as close as it can get. And so you can see this minimum value occurs when x has a value of 1.7320497 approximately. But the y value is actually the minimum value. So that's -19.78461. Now that's, in this area, the lowest that this graph ever goes. You can see, if you look back to the left of the y-axis, this graph is actually going to go lower because there's a part of the graph that goes down towards -infinity forever. But this is what's called a local minimum. So it would be -19.78461 approximately would be the minimum value. Now what about the maximum? Well, now we can go back to second, and we can hit the trace key again. And this time, if we want to calculate a maximum, we go down to 4, or we can just type in the number 4, press enter, and now you can see the cursor again blinking. So what you want to do, it wants us to establish, well, let's see. Let's get on the other side and let's try this again. Okay. So we have second and trace, and we're going to choose 4 and enter, and it's going to ask for a left-hand bound. So it actually took that as my left-hand bound. So there we go. And then I'm going to scroll on the graph and watch the cursor go up and over that point where we think it looks like it's the maximum value, over the hill there, and press enter to establish a right-hand bound. And of course you see the arrows going up there on the graph again. And it's asking, do you want to guess? So you can if you want to, or you can just keep pressing enter. But you could go to where you think it looks like the maximum point and say, I'm going to guess this is it. Press enter. And it will tell you what the closest they can get to approximate the maximum. And again, it would be the y value that really represents the maximum value here, and that's 21.78461. But it occurs when the x value is negative 1.73205 approximately. But again, when we're looking for the minimum or the maximum values, and in this case they're actually called local minimum or maximum because they're the ones that are in this particular area that we established with our boundaries, the local maximum would be about 21.78461. So go ahead and give example B a try, and you can tune back in after you give that one a shot, see if you can calculate the maximum and minimum values, and check your work. Okay, so I hope you've mastered the calculator to find the maximum and minimum values. And so here is the maximum value for that function x cubed minus 2x minus 3. It's approximately negative 1.911338. And the minimum, or the local minimum, is negative 4.088662. Okay, so finally we're going to look at an application. And this one is related to art. So an artist plans to construct an open box from a 15-inch by 20-inch sheet of metal by cutting squares from the corners and folding up the sides. Find the maximum volume of the box and the corresponding dimensions. Okay, so we've got this rectangle that is 20 inches on one side and 15 inches on one side. And we want to know what the volume is that this box will hold when it's completed, and what this volume, or what this box is going to look like. It's going to be sort of like, say, a shirt box without a top on it. And how this shirt box is created is by taking this rectangle and cutting out corners on every corner of the rectangle, and then sort of folding along where these dotted lines would be, and you can kind of just see them, you know, if you kind of fold up the sides on either way, then you kind of can tape those edges together and you've created this little box. Well, we don't know what size of these little squares they're going to cut out. So we're going to just say this is an unknown length, so we'll call it x, so which means this dimension is x right here and this dimension is x right here. So we're going to just like cut this little piece right out, and we're also going to cut this little piece right out on the same dimensions on this side, same down here and down here. So when we think about the volume, we know that the volume is the length times the width times the height. And so if we thought about the length of this thing, so if we were to fold this back together, then the length actually of this box is not going to be 20 inches, it's going to be 20 inches minus, so this part right here would actually be 20 inches minus an x on either end, so minus 2x. Now the width, instead of being 15 along the side, it's actually this length now. And that's because we took 15 and subtracted an x off either end. So that's 15 minus 2x. And then finally the height. Well, the height is actually going to be this dimension right here. See this dimension right there? When you fold that up, that's going to create the height of the box. And so the height is x. So the volume turns out to be, when I expand out these two binomials and multiply the x through, will be, let's see, 20 times 15 is 300, so that's the first two. Outside 2 would be minus 40x. Inside 2 would be minus 30x. The last two would be plus 4x squared, and all of this is going to get multiplied by x when we're done. So I'm going to group my like terms together. So I've got, and put it in descending order of power. So I really have x that I'm going to multiply by 4x squared minus 70x plus 300. So if I distributed that x through, basically would just raise the power on the x on the variable on each one of these and add an exponent on the end. So it would be 4x cubed minus 70x squared plus 300x. Let me just rewrite this up here again. And so this is our volume function, and all we would have to do was graphing calculator, and then we'll go and put it in the calculator, and we'll look for the maximum. We'll look for the relative maximum, and that'll give us the that value of x that would create the largest volume we could possibly get out of this box. So again, just kind of go through that process that we just looked at on how to calculate the maximum value. Put this in as your function and calculate the max. So I went ahead and graphed that, and I might adjust the window quite a bit because the maximum value was very high up on the graph. And so I ended up changing the window range to the y maximum to be up to 400. But then I could see the maximum value, that change in direction, and using the stat calculate and maximum function, I was able to identify the local maximum to be x is 2.83 and y is 379.04, and that would be cubic inches. So in other words, when x, that little cutout piece, is about 2.83 inches, then the volume will be its maximum amount, which will be 378.04 cubic inches of space inside that box. So that does it for today's lesson. I will see you in class.